In 1935, Albert Einstein published two papers that seemed completely unrelated. One described spooky action at a distance, quantum entanglement. The other described wormholes, bridges through space-time connecting distant regions of the universe. For 78 years, physicists treated them as separate ideas. Then in 2013, Leonard Susskind realized something impossible. They're the same thing. Entanglement S geometry. Wormholes A quantum mechanics. This is the story of how one insight unified the two pillars of modern physics. To understand why this matters, you need to know one thing about Leonard Susskind. He spent his entire career fighting impossible battles. The black hole war against Stephen Hawking. 28 years the anthropic landscape debate still going, and in 2012 he was facing yet another crisis, one that threatened to destroy everything he'd built, the firewall problem. Here's the quick version. In 2012, four physicists, Almary, Merolf, Polchinski, and Sully, collectively known as AMPS, published a paper claiming that black hole horizons must be surrounded by firewalls, walls of infinite energy that would incinerate anything crossing the event horizon. Not eventually, instantly. If they were right, Susskind's entire framework for solving the black hole information paradox, his 1993 black hole complementarity principle, was dead. 2 decades of work gone. Susskind knew they were wrong. He had to be wrong. But he couldn't explain WHY. Now, most physicists would have doubled down on the math, buried themselves in calculations, tried to find the technical error in the AMPS argument. But Susskind has never been a conventional thinker. He grew up in the South Bronx. His father was a plumber. He didn't come from academic royalty. He came from a world where you solve problems by thinking differently. So instead of attacking the firewall head-on, Susskind did something radical. He went for a walk. According to Susskind's own account in later talks and papers, he was on sabbatical in Northern California, walking on a beach when the solution hit him. Not from equations, from a pattern, a historical accident that had been hiding in plain sight for 78 years. In 1935, the same year, Albert Einstein published 2 papers with collaborators. The first, with Boris Podolsky and Nathan Rosen, attacked quantum mechanics. It described entanglement, 2 particles connected such that measuring one instantly affects the other. Even across the universe, Einstein called it spooky action at a distance and argued it proved quantum mechanics was incomplete. The second paper, with just Nathan Rosen, proposed something entirely different: bridges through spacetime, mathematical shortcuts connecting distant regions of the universe. Today we call them Einstein-Rosen bridges. You probably know them as wormholes. 2 papers, 2 phenomena, both from Einstein, both from 1935. And standing on that beach, Susskind realized they're the same thing. Wormholes air entanglement. Entanglement creates geometry. The 2 great theories of the 20th century, general relativity and quantum mechanics, aren't separate. They're 2 descriptions of one phenomenon. Susskind called it ER EPR. Einstein-Rosen equals Einstein-Podolsky-Rosen. It was one of those ideas so simple, so obvious in hindsight, that it seemed impossible nobody had seen it before. And if it was right, it didn't just solve the firewall problem. It unified physics itself. But here's the thing nobody tells you about revolutionary ideas in physics. They don't matter unless you can prove them. Let's back up. To understand ER EPR, you first need to understand what Einstein was actually worried about in 1935. Quantum entanglement is weird. Not kinda strange, weird, fundamentally, break your brain weird. Here's the simplest version. Imagine you have 2 particles, let's say 2 electrons created together in a specific quantum state. These particles are now entangled. If you measure the spin of one electron and find it spinning up, the other electron, no matter how far away, will instantly be down. Not because they communicated, not because information traveled between them. They just are. Einstein hated this. In the EPR paper, Einstein-Podolsky-Rosen, 1935, he used this spooky action at a distance to argue that quantum mechanics must be incomplete. There must be hidden variables, he said. Some deeper reality we're missing. He was wrong about that. Quantum mechanics is complete. Entanglement is real. Experiments have proven it over and over again. But Einstein was asking the right question. How does entanglement work? The standard quantum mechanics answer is shut up and calculate. The math works. Don't ask what's really happening. Just predict the outcomes. Susskind has never been satisfied with shut up and calculate. Now, fast forward to 2012, the firewall problem. The AMPS argument went like this. When a black hole forms and starts radiating Hawking radiation, the radiation is entangled with the stuff that fell in, the stuff now inside the black hole. That's what preserves information. Entanglement between the inside and outside. But here's the problem. As the black hole keeps radiating, older bits of radiation start to become entangled with NMR bits of radiation. You end up with radiation entangled with ITSELF, and quantum mechanics says a particle can only be maximally entangled with another system at a time. Something has to give. AMPS said, the entanglement between radiation and the interior must break. And when it breaks, Einstein's equations say you get infinite energy at the horizon. A firewall, anyone crossing the event horizon gets vaporized instantly. This was a catastrophe for Susskind's complementarity principle. Complementarity said there's no drama at the horizon. An infalling observer crosses smoothly, no infinite energy, no wall of fire. Meanwhile, an outside observer sees information preserved in the radiation. Two descriptions, both valid, no contradiction. Firewalls destroyed that picture. If there's infinite energy at the horizon, the infalling observer is DEA'd, complementarity is broken. Susskind needed a way out. He needed to explain how entanglement could connect radiation to the black hole interior gut creating a firewall. And that's when he remembered Einstein's OTHER 1935 paper. The Einstein-Rosen bridge, the wormhole paper, described something bizarre. You could have two regions of space-time arbitrarily far apart connected by a throat. A geometric tunnel through space. In the original Einstein-Rosen paper, these bridges were non-traversable. You couldn't travel through them. They'd collapse before you made it across. But the geometry was there, a connection, a shortcut that couldn't quite be used. For decades, physicists thought of wormholes as a curiosity, a mathematical trick, not something that actually existed in our universe, definitely not something related to quantum mechanics. But Susskind started thinking, what if wormholes aren't separate from quantum entanglement? What if they're the same phenomenon, viewed through different lenses? Here's the key insight. When two particles are entangled, they're connected, not by a signal, not by information traveling through space. They're just connected. Quantum mechanics describes this connection as a correlation in the wave function, an abstract mathematical link. But general relativity, Einstein's theory of gravity, describes reality as geometry, spacetime itself, in GR. Connections are geometric. They're bridges, throats, tunnels through spacetime. What if entanglement doesn't just create a correlation? What if it creates geometry? What if every pair of entangled particles is connected by a tiny non-traversable wormhole? That's ER EPR. Einstein-Rosen bridge is a wormhole. Einstein-Podolsky, Rosen correlations, entanglement, not a metaphor, not an analogy, an identity. When two black holes are entangled, which happens naturally in certain quantum states, they're connected by a wormhole. The interior of one black hole connects smoothly to the interior of the other. And here's the kicker, this solves the firewall problem. If entanglement creates geometry, then the Hawking radiation isn't just abstractly correlated with the black hole interior. It's geometrically connected to it, through wormholes. Tiny quantum wormholes threading through space-time. No need to break entanglement. No infinite energy, no firewall. The infalling observer crosses smoothly. The outside observer sees information preserved in the radiation. Complementarity survives. But to prove this wasn't just a beautiful idea, to show it was actually physics, Susskind needed backup. He needed someone who could work through the details, check the math, make sure this wild conjecture actually held together, he called Juan Maldacena. Juan Maldacena is one of the most brilliant theoretical physicists alive. In 1997, he'd revolutionized string theory with the ADAS-CFT correspondence, a precise mathematical duality between gravity in one spacetime and quantum field theory in another. If anyone could tell Susskind whether ER EPR was genius or nonsense, it was Maldacena. According to Suskind's recounting, the phone call went something like this: Juan, I think I figured it out. ER equals EPR, wormholes AR entanglement. Long pause. Holy shit, Lenny, write it up. What followed was one of the most exciting collaborations in modern physics. Susskind was at Stanford. Maldacena was at the Institute for Advanced Study in Princeton. They worked together remotely. Emails, phone calls, video conferences, building the case for ER EPR step by step. The core idea was simple, but the implications were staggering. Let's start with the simplest case: two entangled black holes. Imagine you create a pair of black holes in an entangled quantum state. This is possible. You can do it in theory by starting with entangled matter and letting it collapse into black holes. The resulting black holes inherit the entanglement. Now, if ER EPR is true, these two black holes aren't just abstractly correlated. They're connected by an Einstein-Rosen bridge, a wormhole. You could draw a spacetime diagram where the interior of black hole A connects smoothly to the interior of black hole B. This isn't science fiction. This is what the math predicts. But here's where it gets really interesting. This wormhole is non-traversable. You can't jump into black hole A and pop out of black hole B. If you tried, the wormhole would collapse before you made it through. You'd hit the singularity and die. So what good is a wormhole you can't travel through? It's not about sending signals. It's about geometry. It's about what entanglement may ends. For 70 years, physicists have described entanglement as a spooky correlation, a weird quantum thing that has no classical analog. But ER EPR says entanglement DOEs have a classical analog. It's a wormhole. It's geometry connecting two regions of spacetime. Entanglement isn't magic. It's the curvature of space itself. Now here's the truly radical part. If this works for black holes, it should work for EVERWHING. Every pair of entangled particles, every EPR pair ever created in a lab, every photon pair from parametric down conversion, every electron pair in a singlet state should be connected by a tiny Einstein-Rosen bridge. A microscopic wormhole far too small to ever traverse, but geometrically real. Think about what that means. When you entangle two photons in a lab and send one to Alice in Boston and one to Bob in Tokyo, you're not just creating an abstract quantum correlation. You're creating a geometric connection through spacetime, a thread, a tunnel, linking two locations through the fabric of the universe itself. Susskind and Maldacena worked through the math. They checked it against known results in quantum field theory, string theory, and general relativity. And everything fit. The conjecture held together. In 2013, they published the paper, Cool Horizons for Entangled Black Holes. The title is Classic Susskind, a deliberate contrast to firewalls. The horizon is cool, no infinite energy, no incineration, because entanglement isn't breaking, it's creating geometry. The paper lays out the argument step by step. Step 1T. Two maximally entangled black holes are connected by a smooth, non-traversable Einstein-Rosen bridge. Step 2. This is consistent with all known principles of quantum mechanics and general relativity. Step 3. The infalling observer crosses the horizon smoothly and follows a geodesic through the wormhole interior. Step 4. The outside observer sees information preserved in Hawking radiation via entanglement with the interior, which is now understood as a geometric connection. Step 5. ER EPR generalizes beyond black holes. All entanglement may correspond to wormhole geometry at some fundamental level. Now, let's be clear. This is still a conjecture, not a proven theorem. Susskind and Maldacena weren't claiming they'd solved everything. They were proposing a new way to talk about entanglement and geometry. But the idea resonated immediately. Why? because it did something physicists had been trying to do for a century. It unified quantum mechanics and general relativity. Not in the usual sense, not by modifying one theory to fit the other, but by showing their two languages describing these same phenomenon. General relativity says geometry is real. Spacetime curves bends connects. Quantum mechanics says entanglement is real. Correlations exist between distant systems. ER EPR says these aren't separate facts. Geometry is entanglement. Entanglement is geometry. And here's the beautiful part: this idea connects to nearly every major theme in Susskind's career. The holographic principle. It says information in a 3D region is encoded on a 2D boundary. EPR gives a geometric reason, WHY. Because entanglement between bulk and boundary creates wormhole connections. The boundary isn't just storing information ABO, the bulk. It's geometrically connected to the bulk. Black hole complementarity. ER EPR explains how the infalling and exterior descriptions can both be valid without contradiction. They're describing the same wormhole geometry from different perspectives. Even string theory fits. In SCFT, Maldacena's 1997 breakthrough, the equivalence between gravity and quantum field theory is now understood partly through ER EPR. Entanglement in the boundary field theory creates bulk geometry via wormholes. It's all connected, but the wildest implication is this: if ER EPR is true, then spacetime itself, the stage on which all physics plays out, might be emergent from entanglement. Space isn't fundamental. It's woven from quantum correlations. The universe is a tapestry of wormholes connecting entangled particles across vast distances, creating the illusion of three-dimensional space. This isn't proven, but it's where ER EPR points. And it's one of the most profound ideas in modern physics. When Susskind and Maldacena's paper came out in 2013, the physics community's reaction was complicated. Some people loved it immediately. The idea was so elegant, so conceptually beautiful, that it felt true even before all the details were worked out. Ed Witten, widely considered the greatest living theoretical physicist, called it one of the most important insights in recent years. Others were skeptical. Where's the proof? How do you test this? If you can't traverse these quantum wormholes, how do you know they're really there? Isn't this just replacing one mystery's entanglement with another mystery, wormholes? And some physicists thought Susskind and Maldacena had lost the plot entirely. Wormholes connecting EVRO entangled pair, that's insane. We create entangled particles in labs every day. Are we really creating millions of tiny wormholes threading through the universe? Susskind's response: characteristically direct, yes, that's exactly what we're doing. The debate has continued for over a decade now. And here's the thing, it's not a debate like the Black Hole War. This isn't Susskind vs. Hawking, two opponents fighting to the death. This is collaboration, refinement, testing the idea from every angle. Since 2013, hundreds of papers have been published exploring ER EPR. Some extend the conjecture. Some find edge cases where it seems to fail. Some propose experimental tests, though testing quantum gravity with current technology is nearly impossible. Let me give you a sense of where the research has gone. First, the firewall problem. ER EPR didn't kill the firewall debate, but it shifted the terms. The AMPS argument assumed entanglement is purely an abstract quantum correlation, but if entanglement creates geometry, the whole calculation changes. You're no longer asking, can a particle be entangled with two systems? You're asking, can a region of spacetime be geometrically connected to two other regions? And the answer might be yes. In general relativity, spacetime can have incredibly complex topology, multiple connections, wormholes branching and merging. ER EPR suggests the quantum state of Hawking radiation creates a geometric network, a web of wormholes connecting the radiation to the black hole interior. No need for firewalls. The geometry handles it. Second, the holographic principle. Remember, Susskind Co. discovered holography in 1994. The idea that information in a 3D region is fully encoded on its 2D boundary. ER EPR gives this a geometric interpretation. In SCFT, the boundary field theory is quantum mechanical. It has entanglement. If ER EPR is right, that entanglement creates wormholes in the bulk, the 3D space. More entanglement to more connectivity, more spacetime. In fact, there's a precise relationship. Researchers like Van Ramsdonk Swingle and others have shown that the entanglement structure of the boundary determines the geometry of the bulk. Disconnect the entanglement and spacetime falls apart, literally. This is sometimes called entanglement builds spacetime, and it's a direct descendant of ER EPR. Third, quantum information theory. ER EPR has become a bridge between physics and computer science. If entanglement is geometry, then quantum information, qubits, quantum gates, quantum circuits, has a gravitational interpretation. Susskind's later work on computational complexity builds directly on this. The complexity action conjecture says that the computational complexity of a quantum state corresponds to the classical action of spacetime in the Wheeler-DeWitt patch. In other words, quantum computing and spacetime geometry are two descriptions of the same thing. Black holes aren't just the densest objects in the universe, they're the fastest quantum computers, and ER EPR is the key to understanding why. But here's what makes ER EPR so powerful. It's not just an abstract idea. People have started testing it. In 2022, Susskind was part of a team, including Adam Brown, his longtime collaborator, that used Google's quantum computer to simulate wormhole dynamics. They created an entangled state, performed specific quantum operations, and showed that the resulting behavior matched what you'd expect from a traversable wormhole in a simplified toy model. This wasn't a real wormhole. It was a quantum simulation. But it showed the connection between entanglement and wormhole geometry isn't just philosophy. It's measurable, testable. The paper was published in Nature, one of the most prestigious journals in science, and it made headlines around the world. Scientists create a wormhole in a quantum computer. Of course, the headlines were misleading. They didn't create a wormhole you could travel through, but they demonstrated that the ER EPR correspondence holds in a controlled quantum system. It's a proof of concept, and it's just the beginning. So what does ER EPR mean for our understanding of reality? Let's start with the most immediate consequence. It changes how we think about entanglement. For a century, entanglement has been treated as a purely quantum phenomenon. Something weird, something that has no classical analog. But ER EPR says that's wrong. Entanglement does have a classical analog. It's geometry. It's the curvature and connectivity of spacetime itself. This doesn't make entanglement less weird. If anything, it makes it more profound. It means that quantum mechanics isn't separate from the fabric of space. Quantum correlations are the fabric of space. Second implication, spacetime is emergent. If entanglement creates geometry, then space itself isn't fundamental. It's a collective phenomenon arising from quantum correlations. At the deepest level, there's no space, no distance, no separation, just a web of entanglement, and the geometry we perceive is the pattern that web creates. This idea, emergent spacetime, is one of the hottest topics in quantum gravity right now, and ER EPR is the clearest articulation of how it might work. Third, ER EPR unifies general relativity and quantum mechanics in a way nobody saw coming. For 100 years, physicists have been trying to merge these two theories. String theory, loop quantum gravity, causal sets, all different approaches to quantum gravity. But most of these approaches try to modify the theories to find a deeper framework that contains both. ER EPR takes a different route. It says the theories are already unified. We just didn't realize it. Entanglement and wormholes are the same phenomenon. Quantum mechanics and general relativity are two languages describing one reality. It's not a final answer. We still don't have a complete theory of quantum gravity, but ER EPR is a guiding principle, a north star. And fourth, this one's my favorite, ER EPR connects to the black hole information paradox in a beautifully circular way. Remember, Susskind came up with ER EPR to solve the firewall problem, which was a crisis for black hole complementarity. which was Susskind's solution to Hawking's claim that black holes destroy information. The whole arc of Susskind's career, from the black hole war in the 1990s to ER EPR in 2013 to quantum wormhole simulations in 2022, is one continuous story. Each insight builds on the last. Each crisis forces a deeper understanding, and the central question is always the same: what happens to information? ER EPR's answer: information is preserved because entanglement creates geometry, and geometry connects the radiation to the interior. The information isn't destroyed, it's geometrically linked across spacetime. Hawking was wrong, Susskind was right. And the reason Susskind was right is that reality is stranger and more connected than anyone imagined. Now, I should be clear, not everyone agrees with ER EPR. There are still open questions. How exactly do you reconcile non-traversable wormholes with the no communication theorem in quantum mechanics? Can you generalize ER EPR beyond maximally entangled states? What about mixed states or partial entanglement? These are active research questions. Physicists are still figuring it out. But here's what's undeniable: ER EPR has changed the conversation. It's opened new research directions. It's connected ideas that seemed unrelated, and it's given physicists a new way to think about the deepest structure of reality. Susskind is in his mid-80s now, still publishing papers, still teaching at Stanford. His most recent work extends ER EPR into de Sitter space, the geometry of our actual universe. He's asking if our universe has a cosmological horizon due to dark energy. What does ER EPR tell us about the entanglement structure of the cosmos? He doesn't know the answer yet. Maybe nobody does. But that's the beauty of physics. The questions never run out. Here's the thing about ER EPR that I keep coming back to. Einstein spent the last decades of his life searching for a unified field theory. He wanted to merge gravity and electromagnetism into one framework. He never succeeded. And he died convinced that quantum mechanics was incomplete, that God does not play dice. But in 1935, in those two papers, EPR and ER, Einstein planted the seeds of the unification he was searching for. He didn't see it. How could he? The tools didn't exist yet. Hawking radiation wasn't discovered until 1974. Black hole thermodynamics wasn't understood until the 1970s. String theory, ADASC CFT, holography, none of it existed in Einstein's lifetime. But the clue was there, sitting in two papers published the same year: entanglement and wormholes. It took 78 years for someone to connect the dots. Leonard Susskind didn't set out to vindicate Einstein. He set out to solve the firewall problem, to save complementarity, to understand black holes. But in doing so, he uncovered something Einstein might have appreciated: the two great revolutions of 20th century physics, quantum mechanics and general relativity, are not at war. They're not incompatible. They're two sides of the same coin: entanglement is geometry, geometry is entanglement. And if that's true, then reality is far more interconnected than we ever imagined. Every entangled pair of particles, every quantum correlation, every bit of information shared across space, all of it is weaving the fabric of space-time itself. We live in a universe held together by wormholes, billions upon billions of them, threading through the quantum foam, connecting everything to everything else. You and I, right now, are part of that tapestry. In physics, the deepest truths are often the simplest: ER EPR. 3 letters, 1 equals sign, a conjecture that unifies the universe. Einstein's two 1935 papers don't just describe one phenomenon, they describe reality itself.